It's a couch right here.
Hey, is anyone sitting right there?
You're that guy.
Yeah, we are.
Maybe some I think I'm not the only one. I
we deleted everything.
Oh, that was really fast. Okay. Hi. In case you don't know who I am, my name is Dr. Ortiz. I am the mathematics professor down in the QRC. Who's heard of the QRC? Everybody? Okay. In case you have never been to our website, I'm going to write that up here really quick. USAFA.mywconline.com. The first time you go there, it will ask you to register for an account. After that, you should be able to log in and see the schedule of all the professors down in the QRC for physics, chemistry, engineering, math, of course, and also the writing center is on there as well. Any big events we do like this, like the Target ADI, which, by the way, wow, lots of people had no idea it was going to be this great of attendance, which I'm happy about, but that tells me that we need a bigger room next time. I'm planning to do 5 of these this semester, so this is number 1 of 5. All right? Okay. So the goal of today is to talk about, now that you've learned all of the 5 series tests, how do you know which one to use? When is one going to be a more efficient or easier choice than another? When is it a bad idea to use a test, and what trouble can you run into? And also, of course, we know on your GRs, you don't get just graded on the answer, but also how to communicate. So I'm going to go over how to communicate all of these tests as well. Okay. Yeah, come in, sign in, and have a seat, if there is one. It seems like it's not. Okay. So, before we actually start with the series tests, I want to point out that on the GR, as you saw on your quiz, you're still responsible for convergence of a sequence, okay? So by the time that we spend, 90% of class time on the series tests, it's easy to forget that, oh yeah, we learned about sequences too. So I want you to be aware of that on the GR, you could still be asked if a sequence converges or not. So I want to start with that real quick before we jump into the series test. So, how do you know if a sequence converges? Anybody? Yeah.
Is it if the limit approaches a number that's not 0 or infinity?
Yes.
Nice, McCall.
Thanks.
So if the limit as n goes to infinity of, should I put a sub n or sigma a sub n? Yes, a sub n. What does the sigma actually mean? It means sum. So if you write sigma, you're talking about a series, okay? So if I want to test what the sequence is going to, I should not put a sigma on there, okay? And so he was right. If the sequence goes to a number, any number, then the sequence converges. And in fact, it converges to that number. All right? So if the terms or the sequence go to a number, then that's good enough for the sequence converging. So you could be given a sequence in set notation. And so if I'm asking if the sequence converges, I'm basically saying what happens to this list of numbers as n gets big. So if we continue into the right, into that list with the pattern, okay, what would you guys say the limit is of this first sequence as n goes to infinity?
Infinity.
Infinity, okay. So the limit of my terms is infinity. Is infinity a number? No. So the sequence does not converge, so we say the sequence diverges. Okay. The next one, does that one have a limit that's a number?
Yes.
Yeah. So for number 2, the sequence does have a limit that's a number. What is that number? 1. Okay. So the sequence converges, which is already a true statement, but I can say a little bit more. I can also say that the sequence converges to 1. Okay? Now this one's a little bit different, but what if my sequence alternates? Can I say the limit is both 1 and -1? No, the limit can only be one number. So in this case, what should I write as the answer to the limit?
Does not exist.
Yeah, it does not exist. Okay. So, of course, does not exist is not a number. The sequence has to go to a number in order for it to converge. So I would say the sequence diverges. Okay. Now you could also be given a sequence in explicit formula notation. So I could just give you a formula for A sub n instead of actually listing out the numbers and expecting you to notice a pattern. Okay. So let's say I give you a formula. And again, the question is, does the sequence converge, yes or no? So I want to take a limit. What are the options in Calc 2 for how to communicate taking a limit? Somebody said L'Hopital's rule is an option, yes. So I'm just going to write this. Yes. How do I know I'm allowed to use L'Hopital's rule? Because it either has to be 0 over 0 or infinity over infinity. This one happens to be which? Provided that I'm going to let n go to infinity. Yeah, it's going to end up being infinity over infinity. Is that the only way you can evaluate the limit? You can also use algebra. Yeah, dividing by the highest term from the denominator. So I can use algebra. Okay. Is there any other way?
Can't you use, I don't know what it's called, but like the polynomial test or something? Logic. Yeah.
Logic.
That's the one. Yeah.
Logic. Yes. Okay, so again, I said part of this lecture was going to be how to communicate. All right? So I want to be very honest with you what the expectations are for limits in Calc 2 versus Calc 1. In Calc 1, you had to show your work one of the two ways. So you either had to use algebra to simplify the limit and evaluate, or you had to use L'Hopital's rule. In Calc 2, since we know that you all went through Calc 1 and had to show us all that wonderful work about how to evaluate the limit, we now trust that you understand how to do it, okay? So you are allowed to use any of these techniques and not show the work. However, what happens if you get the wrong answer and don't show any work? Negative points? Somebody said negative points? No, not negative points.
You can't find where we messed up.
If you get the wrong answer and you don't show your work, you lose the opportunity for any partial credit. Okay? So, does anybody have a logical way to evaluate this limit?
3 over 5.
Yes.
Looking at the coefficients, because they have the same degree.
Okay, so you're using a shortcut that says if the degree of n matches on top and bottom, so same highest degree, then we can take the ratio of the coefficients. Anybody learn that?
Yes.
Okay, quite a few people. Okay, so then what's the answer using that shortcut method? Okay? So because that's the right answer, I'm not going to be penalized for not communicating how I got that. Okay? Now, let's say I make a goofy... Okay, I'm going to put back the right answer here in just a second. Let's say I goofed and just kind of inverted it in my head. But I didn't show the work. I just lost my opportunity for partial. Okay? So, Another way to logically get these answers is not just the shortcut of matching the coefficients. We're also using the idea of dominant terms, okay? And this is going to come back up when we review the limit comparison test. So in the numerator, as n goes to infinity, would you guys agree that 7n is much less significant than the 3n squared? Remember, n is getting infinitely large, okay? And of course, the 3n squared is more dominant than the plus 1, okay? So as n goes to infinity, 3n squared becomes the most important or most dominant term in that numerator, okay? So in other words, the other two terms, 7n and 1, can be considered lesser terms, okay? Insignificant in comparison. In the denominator, what would be the most dominant term? 5n squared. So the n and the plus 1 are basically insignificant in comparison because n is getting so large. So we can also think about this logically, that the limit behaves like simply the dominant term. So 3n squared over 5n squared, which would go to 3 over 5. Okay? Now let's say you were uncomfortable with the logic way and you really wanted to show your work. Well, then we have algebra or L'Hopital's rule. If you're going to use algebra, then what you want to do is divide all the terms by whatever's causing the denominator to go to infinity. So in this case, it would be the n squared, because of dominance, would be causing the entire denominator to go to infinity. So we divide that out. So we would take every single term and divide by n squared. N over n squared, 1 over n squared, 5n squared over n squared, and then simplify it. So this is the algebra way, if you want to show your work. Okay, and now we have a bunch of terms that have that number over infinity form, which we know number over infinity is going to approach what? 0. So this one goes to 0, this one goes to 0, this one, and we're left with 3 over 5, as we knew, okay? Now, I'm only going to show this once, okay? All the rest of the limits we evaluate, I'm just going to use the logic way, and I'll know that you guys know your options from here on out. But one last option, we have L'Hopital's rule. Now, L'Hopital's rule involves derivatives. Do you guys remember that from Calc 1? Okay. So, you may not remember this because it was back in block 2 of Calc 1, that derivatives only exist when the function is continuous, okay? Well, we have two kinds of variables going on in this block, okay? N, the index, okay, is called a discrete variable. The reason for that is because it can't be equal to all the numbers on the number line, okay? In fact, what are the values that n can be? Just, yeah, I heard it somewhere over here, the integers, okay? N can be 1, 2, well, sometimes 0, but integers, okay? N can't be all the possible real values. So we need a different variable that we're going to use to represent a continuous variable. Continuous, okay? So x is going to be the continuous variable because it can be any value on the number line, not just the integers, all right? And we remember we need continuity in order to compute derivatives, okay? Derivatives only exist when we first have continuity. So because L'Hopital's rule involves derivatives, we need to be operating on a continuous function. So what that would look like, as far as notation, is we would take our original limit we're trying to compute, okay? And we would convert it to its continuous version. Now there is a theorem, you're not required to memorize it from the book, but there is a theorem that says that if we convert our discrete function of the sequence into its continuous version, they share the same limit, okay? So we are using the fact, so note, the limit as n goes to infinity of f of n, so the discrete version of the function, is the same thing as if you compute the limit with the continuous variable, okay? So now that we've converted all the n's to x's, we're free to use L'Hopital's rule, we're free to use derivatives. And the same communication you were required to do in Calc 1 is the same here for L'Hopital's rule. So we would have to identify the form as infinity over infinity form. And we would have to communicate that we're using L'Hopital's rule, so the LH over the MP equals. And what L'Hopital's rule does is it takes each of the functions, top and bottom, and replaces them with their derivatives. So 6x plus 7 over 1 plus 10x. But this is still infinity over infinity form, so we'd have to do L'Hopital's rule one more time. And, whoops, I don't need another equals. And then we would get 6 over 10, which is equal to 3 over 5. Okay, so here are your options for how to calculate a limit with correct notation. So you can use logic, you don't have to show any work, but the downside is if you make a mistake doing that, you're not going to get partial credit. You can use algebra, so divide out from the largest term in the denominator, or you can use L'Hopital's rule, in which case you have to convert to the continuous variable x because you're taking derivatives. All right, so back to the problem we started with. Do I know if this sequence converges or not? Should I compare this to 1? That happened on the quiz a lot. Yeah. Remember, if all I'm asking is if the sequence converges or not, then I'm just looking for if the limit is a number. I don't care if that number is less than 1, greater than 1, equal to 1. All I care about is if my limit is a number, okay? So, the sequence converges to 3 over 5. Okay. I know that seems like a silly thing to say don't use a series test on when you're trying to figure out if a sequence converges, but by the time you get to the GR and you spend 90% of this block talking about series tests, you get a question that says, hey, does the sequence converge? And you are so tempted to use a series test on it. So just remember that figuring out if a sequence converges, all it comes down to is, does the limit equal a number, yes or no? There is no series test that you're doing on that. With that being said, let's jump into the series test. All right. How many do we have again? 5. 5. All right. All right, let's list the series tests in the order that we learned them. Which one did we learn first? Test for divergence. Okay, which, by the way, you are allowed to abbreviate as TFD if you would like. Okay? So, what the test for divergence says is if the sequence, okay, I didn't put a sigma on this, so I'm talking about the sequence. If the limit of the sequence, do I want it to be 0 or not 0? Not 0. Okay, if the limit of the sequence is not 0, then the series, which I can put a sigma on, so the series sigma n, or sigma a sub n, diverges. Okay, It's a very short test. That's all it says. Basically, you're using information about what the sequence does to tell you about what the series does. Okay? So it's really easy to confuse what's going on with the sequence and the series in this particular test because you are using information about the sequence. All right? But the conclusion is about the series. All right? You're using information about the sequence to tell you about what the series does. Question: what if the sequence does go to 0?
It might converge.
Then we don't know. The test for divergence does not tell you anything if the sequence does go to 0, okay? Because it turns out it matters how quickly the terms go to 0. Speed does matter. So if the terms go towards 0, and I'm going to put quotations on this because it's not really a defined term, okay? Quickly. Then the series converges. Okay? If the terms go to 0 slowly, then the series diverges. But here's the problem. Is it easy to tell if the terms are going to 0 quickly or not? No, it's not easy. It's not obvious, which is why we need the other tests, okay? So if your terms do go to 0, then basically you know that your series still has a chance to converge, but we have to use some other test to find it out. Yeah.
That's why we don't rely on it with convergence.
You can't use the test for divergence to conclude convergence ever. The only answer you could possibly give using the test for divergence is the series diverges. Okay? Yeah?
So for the last 2 notes on there, don't put those on the test for like reasoning, right?
Correct.
Okay.
Yes. Yes. No, because that's why I put quotations on it. Did I really define what quickly is? Is that something you could like say, hey, this goes to 0 quickly, therefore I know the series converges? No, because quickly is undefined. But conceptually, I want you to understand that that's why we can't say that, oh, the terms go to 0, so I know the series converges. The reason why we can't conclude that is because the speed does matter, okay? So good point. We can't just say, terms go to 0 quickly, because then the grader's going to be like, what do you mean by quickly? How do you know? And that's a great question. How do you know? Which is why we need all the other series tests. Okay, so there's one of our tests, okay? What is test number 2?
Geometric series.
Okay? We have geometric series. Okay. How do we know that we have a geometric series? So this is actually not called a test. Okay? 3 out of the 5 are actually have test in the name. We have test for divergence, we have limit comparison test, we have ratio test. But then we have 2 special types of series. We have geometric series, we have T-series. So these aren't really tests, they're just a special type of series. So how do we know that we're dealing with this special type of series called geometric? Yeah?
And is the next one?
N is the next one. Okay, so that's one way. So in sigma notation, okay, in sigma notation, you are on the lookout for what we call a geometric term, okay? So a geometric term is going to have a number in the base and an n in the exponent, yes, okay? So our geometric series, we can write in its general formula as a times r to the n minus 1. Okay? So another way to think about what makes a geometric series geometric is the fact that it has this special thing called a common ratio, which we name r. And the reason why it's called common is because it doesn't matter which 2 terms you pick next to each other. I can take the second term divided by the first term, or I could take the third term divided by the second term, or the fourth term over the third term, they should all give me exactly the same ratio, okay? So common ratio. Another way to think about the role of R is it's kind of like a common multiple. It's the number that you continue to multiply by over and over to get from one term to the next, okay? So if your series does not have this common ratio going on, then the series is not geometric. So now we have more information we're going to fill in on this geometric series, but let's go on to the last special type of series, P series. Okay, this one has a special form. Okay, it is 1 over n to the power p. So in contrast to the geometric series, instead of having a common ratio, the P series has a common power, specifically in the denominator. Okay. Now, we need to be able to recognize both of these special kinds of series in the sigma notation and in the expanded notation. What I mean by expanded notation is number plus number plus number plus number plus dot dot dot, okay? So sometimes it's easy to tell what type of series you have in the sigma notation but not in the expanded, or vice versa. So what are some strategies to be able to tell that you have a geometric series, and let's say in expanded notation? So let's say I have 1/3 minus 1/6 plus 1/12 minus 1/24. Okay? Now it'd be nice if the directions said, like some of your homework problems, hey, this is a geometric series, now let's ask you some questions about it. What if on the GR we just gave you a series and said, hey, does this series converge or not? We didn't tell you what kind of series it was. Well then basically, you're looking at, okay, I know we have 2 more tests after this, but so far we have 3 tests available to us. Test for divergence, geometric series, and we have P series. So let's just go in order. Would we be able to use test for divergence? Good, no. And the reason why not is because the terms do go to 0. The sequence goes towards 0, which means that the test for divergence does not tell us anything. We don't know. All right, so then we're thinking maybe this is a geometric series. And for geometric series, we're looking for that common ratio, okay? So 2 ways to look for that common ratio. One, I can just take any 2 subsequent terms, take the ratio between them. So for instance, I could take negative 1/6 and then divide by 1/3, or multiply by 3 over 1. So dividing by 1/3 is equivalent to multiplying by 3 over 1. And I get negative 1/2. Okay? But that's not enough to say that this is a common ratio. I have to try out some other pairs of numbers. So let's say I try 1/12 and negative 1/6. Okay? So I take 1/12 and divide by negative 1/6. Oh yeah, I also get negative 1/2. And then the question is, do I get the same ratio no matter which 2 numbers I pick? If the answer is yes, then yeah, this is geometric. And not only did I figure out that the series is geometric, I also know what R is. Okay? So for this problem, R is equal to negative 1/2. That is my common ratio. It's the number that you multiply by to get from term 1 to term 2, and to get from term 2 to term 3, and so on. Okay? So once I know that my series is geometric, I'm going to need some convergence conditions. Which, by the way, have you guys noticed there's a lot of memorization in this block? Yes. So that is not something you're going to want to leave till, you know, a couple nights before the GR. This is stuff you need to like be practicing, drilling into your head over a couple weeks, not like a couple days. So hopefully you're already on your way to memorizing. So the geometric series, the infinite series, okay, notice there's an infinity on top of the sigma, so I'm talking about trying to add all the infinitely many numbers in the geometric series together. Okay, this can do one of 2 things. The geometric series can converge or diverge. If the geometric series converges, This is the one special series that not only can we say that the series converges, aka adds to a number, we can actually specifically calculate what that number is. That's what's cool and unique about the geometric series. Can anybody tell me what number the geometric series adds to if it converges? 0? Okay, I heard it. So we're a divided by 1 minus r. Yes. Now, that's if the sum exists. Remember, this is a big if. If the sum exists, if we get convergence, then you can calculate the sum. Now, this is dependent on what? It's dependent on, it's dependent on the absolute value of r. Okay? Now, I know there's a lot of memorization, but sometimes it helps to step back and think about it logically for a second, to think about why that condition is the way it is, so it helps with the memorization if it even makes a little bit of sense. Okay? Why would we want r to be small?
So the values get smaller and smaller.
Yes, because r is what you multiply by over and over and over. So if r is less than 1, let's say like 0.9, what happens when you multiply 0.9 times 0.9 times 0.9? The numbers keep getting smaller, right? So when your r magnitude or size, absolute value, is less than 1, what that means is that the terms are going to be getting smaller, which is what you want, okay? Now on the flip side, what if absolute value of r is bigger or equal to 1? Well, bigger than 1 would mean the terms are getting bigger. We don't want that, right? Test for divergence said we don't want that. Okay, we do want the terms to go small if we want a chance for our series to converge. Why would 1 be bad, though? What would r equals 1 mean? It means the terms don't grow or shrink, they just stay the same. But test for divergence says if the terms don't become infinitely small, then our series definitely diverges. So the terms staying the same size is also bad when it comes to convergence. Okay, so our sum basically does not exist if our absolute value of r is greater than or equal to 1. Okay, so I just want to make a note here. Let's say that you had a geometric series and you got an r of, I don't know, 3. Okay, so you know based on this, if r equals 3, that your series would diverge. And then the question is, well, calculate the sum if it exists, right? Have you seen that on website?
Yes.
Something about calculate the sum, and then it says if it exists. Okay. Well, let's say I had a first value of 2. Okay. Oh, we need to define that. A equals your first term. Okay. So let's say I have a first term of 2, and my r is equal to 3. All right. And I say, calculate the geometric series with an a value of 2 and an r value of 3.
Just say it doesn't exist.
Okay? Should I try to do a over 1 minus r?
No.
I should not. Okay? You'd be surprised how many times, though, because the formula is there, it's so tempting to use it. Even though I know that my sum doesn't exist, I know that I have divergence. Okay? So instead of trying to calculate the sum with the a over 1 minus r formula, I should just put does not exist. If you're asked for the sum, okay? If you're asked for the sum. All right. So in expanded notation, the way that you tell you have a geometric series is you take, you look for that common multiple, or you take the ratio between a bunch of different pairs of numbers and make sure you get the same number every time. All right. So, how would I tell that I have a geometric series in sigma notation?
Write out the first 3 terms.
Yes, you could do that. You could do that. You could just convert it from sigma notation back into the expanded notation and then look for the common ratio that way. Yeah.
Well, I know like you can't have like adding or not subtracting.
Right. Okay. So in sigma notation, it's helpful to realize what a geometric term is. So you're looking for numbers at the end. Now, if I give you something like this, then it's pretty easy to tell that that's a geometric series because you kind of are looking for a format like this, right? Okay, but what if I give you something a little bit more complex? Oh. Oh no, it's getting crazy. What's that? Is that a P series? That's not a P series. No. Okay. Fact. Okay, so I want to make this point right now. A geometric term is in the format of a number raised to n. A P term is in the format of a n to a number. So they're opposites of each other. They're opposites of each other. So let's look at all the terms in this really nasty looking series that I just wrote. All right. Are there any P terms in that series? No. Okay. Now there's a constant in there. Yeah, there's a constant. Okay. But what about all the rest of the terms? Are those not all geometric terms?
They are.
Yeah. Now they all have different bases. They're all different geometric terms with different bases, but, and I'm sorry, Cadet Hayden, right? As Cadet Hayden pointed out, as long as there's no addition in between the different geometric terms, then algebraically I can combine this into a single geometric term. It would take a little bit of rewriting, a little bit of rearranging, okay? But I want you to realize that if all of my terms are the same type of term and constants are okay, but as long as I'm not mixing geometric term with P term, and I don't have an addition in between the terms, then really this is nothing but a geometric series, just written a little bit complex. All right. So how would I actually rewrite this into the format we're more used to seeing? Well, all of these geometric terms we can break up into smaller pieces. All right. So the 7 to the n plus 1, for instance, we can break up into 7 to the n times 7 to the 1. And then, the 8 to the negative n, I want to put that on the denominator. So I'm going to move it as 8 to the positive n to the denominator. My goal is to have all of my exponents be exactly the same thing as n so that I then can start combining stuff together. Moving on to the 3 to the n minus 1, I'm going to break that up into 3 to the n times 3 to the minus 1. All right. Let's see, what have I not accounted for yet?
The 4 times negative.
The 4 times, yeah. So I still have a 4, and I still have a negative 2 raised to the n. So now, notice I still have the same number of geometric terms. 1, 2, 3, 4. 1, 2, 3, 4. So my geometric terms, I haven't changed the number of them, but what I have done is I now have them all raised to exactly the same thing, n, so they can be combined. All right? So my single geometric term, let's see, at the top, if I combine the bases of 7 and 3, I'm going to get, I'm going to get 21. And then my bottom should be negative 16. Okay, now I have some constants left over. Let's see, I have a 7. Oh, the 3 should really be in the bottom, so 7 over 12. Okay, so the 3 to the negative 1 is really a 3 in the denominator. 3 times 4 gives me 12. Okay, does this look now more similar to what we're used to seeing for geometric series? Okay, can I identify R now? What is my R? Okay, question, is R negative 21 over 16 or is R 21 over 16?
Absolute value.
Absolute value. 20 over 60.
R equals negative.
R is negative 21 over 16. Now, I know why some of you were giving me the positive version because the convergence condition has that, okay? But R is allowed to be a negative number, okay? okay? So R is in fact negative 21 over 16. Why is it important that you distinguish between the absolute value of R and R? Because if you're asked to calculate a sum, and R happens to be a negative number, notice that in the sum formula, A over 1 minus R, you use the original R value. You don't use the absolute value of R, okay? All right, so let's practice one of our communications here. Let's conclude something about this series. Do you guys know about the TLC acronym? Yes. What does T stand for? Test or series. Remember, only 3 of the 5 tests actually have the word test in them. All right. L is for logic. C is for conclusion. Okay. So I want to make a conclusion about this series here using my TLC communication. So I can do this in a sentence, or I can do it with actually writing the TLC. I'll show you both. All right. So my TLC. So if you want to organize your communication like this, you can do that. So for T, I'm looking for the name of the test, or I'm looking for the type of the series. So which should I put here? Geometric series. Okay. And my logic should be what? Okay. So this is your logic for geometric right there. That's your logic. Okay, so I should say that the absolute value of R equals 21 over 16. Am I done with the logic statement? I have to compare to 1. If you want to get credit for the logic statement, you have to actually finish it. You have to compare to 1. So I should say greater than or equal to 1. Okay? And then for my conclusion, I'm going to make a bad conclusion, so I'm just telling you that right now so it doesn't get into your notes. What is wrong with that conclusion? The word it. If the word it is not clear, what you mean by the word it, then you should not be using the word it. Now, if you've written a whole sentence where it's clear what the subject it is, then that's okay. But here, I've not put this into a sentence where it's clear what it is. So what should I say instead? The series diverges. Okay. Now, if you don't like this and it seems a little clunky, and you'd rather put it into a sentence, then I could say something like this. This is a geometric series with absolute value of R equals 21 over 16, greater than or equal to 1, so it diverges. Why is it okay in that sentence? I said this is a geometric series, so that's what I mean by it. All right. So, yeah, go ahead.
So with the R, if it's not an absolute, like you might say,
Okay.
like R,
Okay, so Cadet Kuname asked about when you do your logic statement for convergence or divergence, should you use R or should you use absolute value of R? Is that what you meant? Okay. You should use absolute value of R because that is the convergence condition. Okay. Now, let me say this again. If you're asked to compute the sum, provided it exists, then the formula you're using is A over 1 minus R, which does not have an absolute value on it. So if you're trying to calculate the sum, you don't use the absolute value. But if you're trying to state whether the series converges or not, then you should be using the absolute value of R. Does that make sense? Okay. All right, so to recap, how do you know if your series is geometric? Okay, you should be able to tell this in both notations. So in sigma notation, you're looking for all your terms either being constants or geometric terms with no addition or subtraction in between. Because as long as there's only multiplication and division, as you saw here, we can do some rewriting and get this back into a single geometric term with a single base r. All right, so I'm going to add that, if I can reach high enough. So all geometric terms and constants, no addition or subtraction between terms. Okay. Sorry about the bad handwriting. I was on my tippy toes there. All right. So, on to P-series. Okay, what are the convergence conditions for P-series? Basically the opposite. Okay? So, I'm going to rewrite this again. Here. So P term. And number. Okay. So, one thing I want to note about P-series is it is a positive type of series, which I'm going to make a small note of again when we get to the comparison test. So, P-series, you're adding a bunch of positive terms together. All right? So, remember, convergence of a series means the series sums to a number. Divergence of a series means that there is no sum, right? The sum doesn't exist. So, if you're adding a bunch of positive numbers together, and your series converges, aka adds to a number, that means that the P-series adds to a number, which is only going to happen if what is true about P?
P is less than 1?
Greater than 1. If P is greater than 1. Now, like I said, I know there's a lot of memorization in this block, but sometimes it helps to think it through a little bit logically so you see why P has to be bigger than 1. We talked about the reason why we wanted R to be small is because you multiply by R over and over and over again in a geometric series. So you want R to be small, okay? Why would you want P to be large? Remember, P is specifically in the denominator. We talked about before, for convergence, do we want the terms to go to 0 quickly or slowly? Quickly. The faster the terms go to 0, the better the chance to converge for the series. So, does it make sense that the bigger P is, that the faster the terms would go to 0?
Yes.
Yeah, okay. So, hopefully that helps you memorize the fact that P has to be bigger than 1 for convergence. So you get converges if P is bigger than 1, and if P is smaller than or equal to 1, you get diverges. Okay? And since the P series is a positive series, and it doesn't add to a number if it diverges, that means it had to have added to positive infinity. Okay? So, again, we have to be able to tell if we have a P series in two different notations. So, sigma notation and expanded notation. All right, I'm going to erase a couple of these examples, but leave up the important information. Okay. All right. So, in sigma notation, it should be relatively straightforward to identify that we have a P series because we're pretty much looking to match to this format right here. Okay? Can anybody tell me what P is for this P series? 3. Okay. So, again, we're going to practice our TLC communication. So, I want to state whether this series converges or not with all the proper justification. So, now I'm going to do it in a sentence first. All right? So, this, okay, is a P series. So, I've already got credit for the T part, right? I mentioned what type of series it is. Now, let's do some logic. So, when P equals 3, am I done with logic?
No.
No, I haven't compared to 1 yet. So, which one am I doing?
Greater.
Greater than 1. So, it converges. I'm okay with the word it here because I already said what it was in the sentence. Now let's contrast that with a TLC, which you're also allowed to use for communication. All right, so for T, I should put what? I should just write P series. All right, L, here's basically, I need to write this statement right here. The fact that P is equal to 3 greater than 1. And my conclusion should be series. I can't use it this time because I haven't made a sentence where it is clear what I mean. So I have to say series converges. All right. So that was pretty straightforward. I can make the sigma notation a little bit more complicated, not as bad as what I did with the geometric one, but a little bit more complicated. Okay? Look what I did. 2 different powers of n. Okay? But kind of like the geometric series, as long as they're all the same type of term and there's no addition or subtraction in between, then algebraically I can combine these 2 powers of n into a single power of n. Okay? So how would I do that? How would I get this down to a single power of n?
N to the 1/2 over n to the 4th,
Yeah.
and then divide them.
So I'm going to move the n to the 1/2 into the denominator, because remember, we need the power of n to be in the denominator. All right? So I can rewrite this as 1 over n to the negative 1/2 times n to the 4th. But I'm still not down to a single power of n. I need to get this into 1 power of n.
N to the 3.
So what we can do is we can add the exponents, right? Like if I took x squared times x cubed, when you add the exponents to get x to the 5th, same type of idea. So this would be equal to the series from 1 to infinity of 1 over n to the 3.5, 3.5. Okay? So that's a p series with p equals 3.5. So does it converge or diverge? Converges. Yes. All right. So the hardest one is probably the expanded notation when it comes to p series. All right. So let's look at a couple examples of that. Okay. So would you agree that series written in expanded notation a lot harder to see if this is a p series going on?
Yes.
Okay. So I'm just going to expand it back out to the 3 tests again. Okay. If I don't know what series I'm dealing with, I'm just going to go one by one. Can I use test for divergence? Can I use test for divergence on any of these?
No.
No, because the terms are going to 0. So if the terms are going to 0, then the test for divergence tells us nothing. All right. So then I'm thinking, well, maybe this is a geometric series. And to know if I have a geometric series in expanded notation, I'm looking for that common ratio. So do I have this, or maybe I should write one more here. Okay. Do I have the same ratio between the first and second term that I do between the third and fourth? No. Okay, so we can't use test for divergence because the terms go to 0. We can't use geometric because there's no common ratio. So we're hoping this is a p series, okay? One thing that's helpful is to know how a p series is written when you expand it out. So this would be the same thing as 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and so on. what's 1 to the p? 1, yes. Okay. So one interesting thing to note, a p-series always starts with 1. So I know I'm not dealing with a geometric series here, and my first term is 1, so that might be some indication that this could be a p-series. All right? The other thing I'm looking for in a p-series is I'm looking for a common power in the denominator. Okay? Do we see a common power in the denominator?
Yeah.
Okay? Not that you know what that power is yet, but does it look like we're applying the same operations to the end values each time? Like, I'm applying the same operations to 2 as I am to 3 as I am to 4. Okay, so same power is being applied. What about the second one? Does this look like it might be a p-series?
Yes.
Yeah. In fact, can we tell what the power is? The second one? 2. Yeah, it's p equals 2. So we should be able to match, well, clearly the 1's match up, okay, the 1's, but I should also be able to match up the 1 over 2 to the p with the 1 over 4. So would you agree that 4 is the same thing as 2 squared? And 9 is the same thing as 3 squared, and 16 is the same thing as 4 squared? So I can rewrite this expanded format back into sigma notation. So I'm dealing with a p-series with p equals 2. All right. Well, how about the first one? Okay, the 1's match. What about the 1 over 2 to the p? So if this is in fact a p-series, I should be able to match up the 1 over 2 times 4th root of 2 with the 1 over 2 to the p. Right?
Yeah.
Okay. So I'm claiming that 1 over 2 to the p is equal to 1 over 2 multiplying the 4th root of 2. So my goal would be to rewrite the power of 2 in the denominator as a single power of 2. So one way to help with that is to recognize that 2 is the same thing as 2 to the 1. And how can I rewrite the 4th root of something?
2 to the 1/4.
Yeah, this is the same thing as 2 to the 1/4. Okay, now I'm closer, but I want to combine this into a single power. So add the exponents, right? What do I get when I add 1 plus a 4th?
5/4.
2 to 5/4. So this would be a p-series. So if I put in sigma format, this would be a p-series. 1 over n to the 5/4, so I would have a p-value of 5/4. Okay? Now the last one, that doesn't look like a p-series because the first value isn't 1, it's 3. But that doesn't necessarily mean that this is not a constant multiple of a p-series. Okay? Yeah, question back there.
Did you mean to put 4 over 64?
What did I do?
On the third one, this would be 4 over 64.
The third piece.
Oh, on the third expanded.
Third.
Yeah, on the last term.
Oh, yeah, thank you. That was supposed to be great. Thank you. Good. All right. So, thank you for fixing that. All right. So if I looked at this series right here and I just didn't know what to do, I would always think about test for divergence first. All right. But the problem with test for divergence is the terms aren't going to 0, so I can't use that. Then I would be thinking about geometric. All right. Well, for geometric to work, I can multiply 3 times 1 over 8 to get from the first term to the second, but the problem is if I multiply by 1 over 8 again, I don't get to the next term. Do you guys see that this is not geometric? Okay, so then I'm thinking p-series, but the problem is I know p-series always start at 1. So what I can do is I can force the first term to be 1, okay, by factoring out that 3. So if I factor out the 3, my first term would then be 1. My next term would be what? 1/8. My next term would be 127, 1 over 27, 164. Okay? So the 3 is a constant multiple in front of the series. What I'm hoping is that the series in the parentheses is a p series, okay? Do we have a p series in the parentheses? Yeah. With p equals what? Yeah, so this is the same thing as 3 multiplying the series 1 to infinity of 1 over n cubed, okay? So what happens if there's a constant multiple of p series? How does that change the logic? Okay, so I'm going to move this over here so you can see it a little bit better. Okay, so we've rewritten this as 3 times a p series. Oh, whoops, that's supposed to be n cubed. Okay, so remember we said that if a p series converges, that means it adds to a positive number. If a p series diverges, that means it adds to infinity. So how does the fact that there's a 3 in front of this make any difference? Okay. If the p series converged, then 3 times a number is still a number, right?
Yes.
Okay. If the p series diverges, then 3 times infinity is still infinity. So the constant multiple in front doesn't really affect the convergence or divergence. But I still should account for this when I'm addressing the communication for what's going on. So I would say, usually I would say, hey, this is a p series with p equals blah, 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 so the series does whatever. But now I'm going to say is a constant multiple of a p series with p equals 3 greater than 1, so it does what? Converges. Okay. So, do you understand the slight difference there? Because the p series actually starts with 1, but now I have a constant multiple of a p series, which doesn't change really what's going on with the convergence as far as the final answer. But I am noting that this is not in fact a p series, it's a constant multiple of a p series. Okay? So, in expanded format, okay, for a p series, you're looking for the series to start with 1, okay? Also, you've probably already ruled out test for divergence and that there's no common ratio, so it's not geometric. So if what you're left with is looking for p series, you're trying to look for something with a common power in the denominator that starts with 1, and if you don't see that your series starts with 1, you can always try factoring out that number to force the first number to be 1, and then you can maybe see the p series a little bit easier. Yeah, question?
So like, let's say that you accidentally skipped a step, or like you saw the 3 down in GR and you thought that maybe it's not a p series, so you jump to the next test, which is like
Okay, so the problem with jumping tests is sometimes you end up doing a test that you're not allowed to do. Okay, so worst case scenario, you do a test you're not allowed to do, and you're probably looking at an F as far as the grade. Okay, so I mean, no, let's be honest here. All right.
So what if you like conveyed all the work for it and it was right? Like,
okay, if you're doing a test you're not allowed to do, there's no way you could be doing it correctly. All right. For instance, if I have something, so this brings us into limit comparison test. All right. So limit comparison test, which you are allowed to abbreviate LCT. Okay. So we talked about you should use a geometric series on a geometric series. You should use a p-series test on a p-series. You should only be doing tests for divergence if your terms do not go to 0. All right. So what if I have something with a bunch of powers of n? All right. Okay? I have a bunch of powers of n. But the problem is now, unlike before, I have addition in between the terms, right? Okay? they're all the same type of term, they're all that n to a number type p term, but I can't algebraically get this into a single power of n because of the addition in between the terms, okay? So the best I can say is that this is similar to a p series because of that addition. Yeah,
Are
question?
you trying to get it to be a p-series?
Yes and no. All right. So I wanted to answer. I'm sorry. What's your name back there? Birdsong. Can I? Oh yeah. Can I have Birdsong? I'm sorry. I remembered that Birdsong because his name is so cool. It's just an interesting last name. Now you're on the video. Sorry. Anyways, the problem with trying to do an actual p-series test on this, right, without doing the limit comparison part of it. If I did, okay, so this is, should I write it in a different color for badness? How about, all right. So if I did this.
Badness.
Right, this is badness. So if I do this, p-series. All right. It's already bad because this is not actually a p-series. Okay, so I'm not allowed to use the p-series condition on anything besides a p-series, right? Okay, now my logic would be to try to identify a p. Now I know that this is going to a kind of a good place. It comes from a good intention, all right? You're trying to figure out what this series acts like as n goes to infinity, right? Okay, well as n goes to infinity, can anybody guess what power of n this acts like? Remember we talked about dominant terms? What's the dominant term in the numerator?
N cubed.
N cubed. Okay, so the rest of them are less significant as n goes to infinity. What about in the denominator?
Into the 4.
Okay, so when we say acts like what power of n, I'm not really including the constant in that. Okay, so yes, I agree the denominator acts like 2n to the 4th, but if I'm specifically asking you what power of n the denominator acts like, you would just say n to the 4th, right? Okay, so as far as comparing this to a p-series, I would say this series acts like 1 over n. Right? If I simplify n cubed over n to the 4th,
So do you have to do like the limit thing?
so 1 over n would be a p-series with p equals 1, which is less than or equal to 1. Okay? So, I mean, the conclusion's right. I am in fact going to compare this to a p-series with p equals 1, and I'm going to conclude that the series diverges. What was the problem though?
You have to get rid of the rest of the stuff.
With this communication, I'm not saying that this is similar to a p-series. I haven't said anything about that. Based on my communication, I'm claiming that this is actually a p-series, which it is not. I can tell you, that will probably get you that grade.
Ooh.
Okay? So how do I actually properly compare this
So limit
to a
as
p-series?
n approaches infinity.
Okay? So let's erase that.
Of
Okay? So when do you want to use limit comparison test? You want to use limit comparison test when you have something that is similar to a p-series and test for divergence doesn't work. Because you can have a series that's similar to a p-series and put yourself through a lot of work of the limit comparison test that is not necessary. Let me contrast this real quick with
test for, they usually test for divergence because you have two of the same
okay.
power.
So, all right. Do you guys see the similarity between these two? They're both series with a bunch of different powers of n, with addition in between, right? So I can claim that they are both similar to a p-series, but one of these, I could use test for divergence and get done with this problem way faster. But one of these, I would be stuck with limit comparison test because test for divergence doesn't work. So, which is the one where test for divergence would work? Yeah, because the limit of the term, the limit of the sequence is 7 over 8. So, what would my TLC be for that one? I would say test, TFD, test for divergence, logic. What do I have to do for logic for test for divergence? I have to actually say what the limit of the sequence is, which somebody said 7 or 8, which we talked about. You can get away with logic with no work shown, provided you're confident in your answer, because if you get the wrong answer, then there's no partial credit because no work is shown. Now, am I done with the logic statement? Just like comparing to 1, for the other 2 tests, I have to compare to 0. So I have to claim that this is not 0. Okay? And then my conclusion would be what? Series diverges. Okay, so is that not preferable to doing a limit comparison test?
Yes.
If you can get away with it? Yeah. Okay, so you should be doing a limit comparison test if A, you have a series that's similar to a p-series, and B, test for divergence does not work. All right? So what do we do to actually prove the similarity? So the part that we are missing, okay, is that we actually have to prove that this series behaves like 1 over n. We didn't prove that. I mean, we think so, but we never proved it. So the idea is, okay, maybe I shouldn't write this under geometric. Can I erase geometric? You guys all have that stuff, right? Okay, we're gonna erase that. Oh.
No, you're fine. He's ignorant. I'm sorry.
Okay.
Nice. Yeah.
All right. So one stipulation of the limit comparison test is we have to be comparing 2 positive terms. So I made a point of the fact that the p-series is positive. So we can always compare to a p-series, okay? Provided that our original series is also positive. So is this a positive series, all positive terms?
Yes.
Yeah, okay, so no worries there. So first, what we want to do is make it very, so I said I'd be hammering on communication. You must say what AN and BN are, okay? You can't have a conclusion that says, hey, this is what the AN series does, this is what the BN series does, and never actually mention what the terms are. So AN should always be your original term, and B sub n should be the simplified term, as n goes to infinity. All right? So for this problem, we're going to let a sub n equal that entire original term. Now I said term, I didn't say series. So for the term, I should leave off the sigma. All right? So a sub n is going to be the original term, but not the series. All right? And b sub n is going to be the simplified term as n goes to infinity, where I don't want to include any constants on my b sub n because I'm trying to make this into an actual p-series term, all right? And so for my p-series term, I just want the power of n. I don't want, you know, the 2 that goes with it. So my most dominant term from the top as n goes to infinity, as we said before, would be n cubed. And on the bottom, yeah, there's a 2, but I don't want that there because I'm trying to get a p-series term, right? So I just want the power of n. So I'm going to leave off the constant there. And then this simplifies into 1 over n.
Hey, ma'am.
Yeah.
So on the test, would you have to write out that a sub n is equal to what's in the series?
Okay, so the question was, for full communication points on a limit comparison test, do you actually have to write what a sub n is? Yes, you do. All right? Because otherwise, in your conclusion statement, you say something about sigma an, and that's never defined. Okay? So you have to actually say what the an and the bn are. All right? That's step 1.
Yeah.
Step 2, we have to prove. Well, we can do this in 2 different orders. We can either say what's happening with the BN series first and then prove similarity, or we can prove similarity and then say what's happening with the BN series. But you do have to prove similarity between the terms. Okay? So I'm going to start with the similarity. So we need to take the limit as n goes to infinity of an over bn, and that could give us one of 3 different questions.
Sorry, don't
Go
you
ahead.
have to prove a BN, like, what, if it covers or diverges by some?
Okay, like I said, there's two different orders we could do this, all right? We can show what the BN series is going to do and then prove the similarity between AN and BN. Or we can prove the similarity between AN and BN and then say what the BN series does. But you're correct, we have to at some point say what the BN series is doing.
I'm sorry.
No, it's okay, question.
Is there any benefit to like real one first?
Personally, I don't think so. I would say the most forgotten step is proving the similarity. So in that sense, if you do it up front, you're less likely to forget it. But no, there's no con to do it the other way around. Okay. So if you got a limit of 0, this would be bad. Okay. If you chose B sub n correctly, we do not expect a limit of 0 because what 0 would mean is that B sub n goes to infinity way faster than A sub n, which would mean that they're not really similar to each other. If one is way bigger than the other, then that's not really proving similarity. So if we get a limit of 0, that's showing not similar. And one of two things happen. Either you picked your B sub n incorrectly, and now the 0 is showing that your B sub n is incorrect, or maybe you picked B sub n correctly, but you computed your limit incorrectly. So something bad is going on if you get 0 as your limit. The flip case is true if you get infinity. This would mean the opposite. This would mean A sub n is way, way bigger than B sub n. So again, this would show that they're not similar. Okay? So anything in between 0 and infinity, any positive number, okay? Any positive number. This would prove that AN and BN are similar as far as convergence is concerned, okay? So as long as the limit of AN over BN is a positive number, this shows that both series are similar enough that they're going to either both converge or both diverge. They're not going to do opposite things for each other. All right, so our goal right now is to prove the similarity between this AN and this BN. So we're going to get the limit as n goes to infinity of the original term. Okay. And whenever I divide by a fraction, I don't really like to write it as divided by 1 over n. That's cumbersome and you end up trying to rewrite it anyway. So instead of dividing by a fraction, I always like to multiply by the reciprocal. So I'm going to multiply by n over 1 instead of dividing by 1 over n. And so if we simplify this, all right, distributing the n through, we'll get n to the 4th. N to the 1/2 times n to the 1 gives us n to the 3/2. And then I get a 2n squared. And my denominator is still 2n plus 3 to the 4th plus 8. Okay? Now, to compute this limit, you could use algebra. That would be a little bit nasty. I probably wouldn't recommend L'Hopital's rule because of the fractional power there. But through logic, we can consider the dominant terms. Now, for this limit, I do care about the constants because I want to compute this limit accurately. Whereas with the Bn, for the simplified term, we're specifically trying to make it into a p-type term, so we didn't want to include constants. Now I need to care about those constants. So my most dominant term in the numerator is n to the 4th. My most dominant term in the denominator is 2n raised to the 4th. So I have to raise that 2 to the 4th as well. Okay? What is 2 to the 4th? 16. So my limit should be 1 over 16. Okay? Because that 2 is being raised to the 4th. So yes,
Why
question.
did we take into account the number 2?
Why did we...
We just said the most dominant term in the denominator is 2n to the 4th.
So the most dominant term in the denominator is 2n all raised to the 4th.
But before we said only n to the 4th.
Correct. So when I was identifying b sub n, all right, we need b sub n to be a p-series term. Okay? That's why we left off the constant. We only wanted to make sure that we had the correct power of n in the denominator. Does that make sense? Now, I guess you could make your BN series a constant multiple of a P series, in which case you could argue that when it gets to that time. But there is not need for that because all we need is AN and BN to perform similarly as far as convergence. And we already know that the constant multiple of a P series, that constant multiple doesn't affect convergence at all. Okay? So in some sense, yes, you could include the constant, you don't need to though. Okay? But when we compute the limit, that constant doesn't matter because we're trying to compute the limit correctly here. Okay? So what was I hoping for to prove similarity again? Any positive number. So 1/16, okay, what I see a lot here is we get so used to comparing to 1 that it's like a knee-jerk reaction to put a less than 1 here. Okay? But in context of what we're trying to show, which is similarity, putting less than 1 wouldn't really mean anything. What should I actually put to show that this is a positive number? I should put bigger than 0. Yeah, because I want to show that this is a positive number. All right? So what we actually just proved is not convergence or divergence. The limit, in the limit comparison test, the purpose of that limit is to prove similarity. So at this point I can say that AN is similar to B sub n. That is what I can say right now. All right? And as Cadet Birdsong pointed out, yeah, I have to still say what's going on with the BN series. So now is that time. All right? So if I were to add up these 1/n terms, that would form a P series. So I'm going to say sigma BN. Why do I have to put sigma? Otherwise, it's not really a P series. It's not a series at all without the sigma. So I'm going to say sigma BN is a P series with P equals what? 1. And then I'm not done with the logic for that. So this is almost like a mini TLC within the overall limit comparison test. So I have to say, okay, that's less than or equal to 1. So it diverges. Okay? So what do we have so far? Oh, by the way, does it make sense why we had to say what A sub n and B sub n were?
Because they both have.
Otherwise, this would have no meaning. Sigma BN, I mean, you would make the greater guess what you meant, but you never want to make the greater guess what you mean. Okay? So we said what AN and BN are. We proved the similarity between them. We now know what the simpler series does because it's a P series. So what is similarity bias then? What was the whole point of proving that AN was similar to BN? They will both do the same thing as far as convergence is concerned. So because the simpler series BN diverged, I can claim by similarity that the AN series does as well. Now, for TLC, did I mention limit comparison test yet? No. So if you haven't mentioned it up front, now would be the time to put it in the conclusion. So I can say, I'm going to erase this stuff here. Okay, we'll finish off. So by the limit comparison test, so you can abbreviate that if you would like. Sigma AN, okay, so now I'm talking about the original series, also does whatever the BN series does. So I would put also diverges. Okay? So again, you can mix up the order a little bit. I would always define the terms first though. That makes the most sense to define those first. If you wanted to say what the BN series did before you proved the similarity, so before you did the limit of AN over BN, that would be okay. You could reverse those two. All right? So when do you want to do a limit comparison test? You want to do a limit comparison test when you have something that's similar to a P series, but test for divergence does not work. Would you agree that this test is shorter than this test?
Yes.
Okay.
Yeah.
So when you have something similar to a P series, limit comparison test might be the way to go, but test for divergence is always something to keep in mind. All right, so I want to note that you can also do a limit comparison test with a geometric series, okay? But I won't be showing you an example of that. Maybe I will after we do ratio test. But, all right. When do you use ratio test? Okay, so test for divergence, you use when the limit is not 0, right, of the sequence?
Yes.
Geometric series you use when you actually have a geometric series. So all your terms are geometric or constants, no addition in between. You would do a p-series condition if you had a no-kidding p-series or a constant multiple of a p-series. Okay? You use limit comparison test when you have a series similar to a p-series, but test for divergence does not work. So when do you think you use ratio test then?
Whenever you have a negative term or number.
Negative term? Exponents.
Just like a little of everything.
A little of everything. Okay, ratio test. So you want to use when you have mixed terms. So what do I mean by mixed terms? Yeah, so basically you have the p-type terms and you have the geometric terms together, right? Because if you have both types of terms, can you really compare to one or the other? Yeah. So limit comparison test doesn't really work if you don't have a particular type of series to compare to. So if I have a mixture of p-type terms, n to a number mixed with the geometric terms, number to the n, then I can't really compare to one or the other. Another good place to use the ratio test is when you have a factorial, okay? And I'm just going to put and test for divergence doesn't work. Because just because you have mixed terms doesn't mean that test for divergence might not work. Okay? Which is why probably you learned it first, because it's a test you should always have in the back of your mind. It's a fairly quick test to use and it's very powerful when it works. Okay, so what does the ratio test say? It kind of acts like the geometric series condition a little bit, okay? Capital L, okay? I'm putting a similar symbol, not an equal symbol here, but capital L kind of behaves like the absolute value of R from the geometric series. Because remember, one way to calculate R was to take A2 over A1, or A3 over A2, or A5 over A4. So, do you see how we're taking the right term divided by the left term? That's kind of like computing R. But if you do that for a series that's not really a geometric series, then you're not going to get the same R every time. It's not going to be a truly common ratio. But if we look at what's happening to the ratio between terms as we let n go to infinity, then we have a better idea of what's going on late in the series, okay, as n gets really, really big. And the reason why we have to have an absolute value is the same reason we had to have an absolute value on our R, okay? So it might make sense that the convergence conditions on capital L are kind of like the convergence conditions for absolute value of R. Remember, if absolute value of R was less than 1, we got what? Convergence. So series converges. Okay, so far this is behaving pretty much like the geometric series. If L is bigger than 1, so remember if absolute value of R was bigger than 1, then we got series diverges. Okay, and if L is equal to 1,
It's inconclusive.
that's where it's different. Yes. So the first two conditions are exactly like absolute value of R, but where it differs is at 1. Okay? Whereas if the absolute value of R is equal to 1, we said that the series diverged, right? For geometric. But for ratio test, we get an inconclusive result. And the reason is because the capital L is not exactly like the absolute value of R. Okay? They're similar, but they're not exactly the same. So, as far as computing this capital L, I'll give you some advice here. and a lot of it has to do with algebra, okay? So you're gonna have to simplify, so that the main setup is you set up the formula for your capital L with the limit, then you're gonna have to simplify the limit as much as you can, and then evaluate, okay? And then when you're simplifying the limit, you're gonna have to simplify between geometric terms, and you're also gonna have to simplify between factorials. So quick review of factorials. So 10 factorial I can write as 10 times 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. Okay, that's a lot of writing. Can I not also write 10 factorial as 10 times 9 factorial? Okay, so you can always rewrite a larger factorial in terms of a smaller one. Okay, let's say that I can use this to try to cancel between 2 factorials. So which one would I want to rewrite? The bigger one. Yeah, the 10 factorial is the bigger one. So I would rewrite the 10 factorial until I got to the smaller one. All right? So you rewrite the larger factorial until you get to the smaller one. And then you cancel out the smaller factorial, which would leave us with 10 times 9, or 90. Okay? Now, what if we try to do this with n's?
Same thing.
Let's say I'm trying to cancel between n plus 1 factorial and n factorial.
Well, n plus 1 factorial is not 2 factorial.
So the n plus 1 factorial is the larger factorial. So I would want to rewrite that one in order to cancel out the smaller one, right? So what is the first term of n plus 1 factorial?
N plus 1.
N plus 1. And then the next term? N factorial. And then cancel the n factorials. Okay? Now, what if I have n minus 1 factorial over n factorial?
You've got an extra n on the bottom.
Which one's the larger factorial then?
The bottom.
The bottom one. So how do I rewrite n factorial? Yeah, you always start off with the highest term, which would be itself, just like the highest term of 10 factorial is 10. So I start off with n, and then go to the next lower term, which is n minus 1 factorial. So this would leave me with 1 over n. All right? So we're going to be using that to make some cancellations. All right. So let's look at an example. Whoa. I have a lot of signals going on to use the ratio test right now. What's one signal about using the ratio test?
Negative.
Factorial.
The factorial, right? Okay, what about mixed terms? Do I have mixed terms going on?
Yes.
Yeah, I have both the n to a number type term and I have the number to an n type term. So for our TLC, we're going to communicate. You can do this either at the front or in the conclusion. At some point you have to mention the ratio test. Okay, so we're going to use ratio test. The logic for a ratio test is simply computing the capital L. Okay, that's all you're doing. So capital L is limit n goes to infinity, absolute value of a sub n plus 1 over a sub n. Okay, how do I get my n plus 1 term? You replace all of the n's with n plus 1's. Okay, all of the n's in the original term become n plus 1. So my 3 to the n becomes 3 to the n plus 1. My negative 2 to the n plus 1 becomes negative 2 to the n plus 1 plus 1. My n to the 4th becomes n plus 1 to the 4th. And my n minus 1 factorial becomes n plus 1 minus 1 factorial. So that is all my a sub n plus 1. But I still need to divide that by the original term. Remember, I don't really enjoy dividing by fractions. I would much rather multiply by the reciprocal instead of divide by a fraction. So I'm going to multiply by the reciprocal of the original term. So we're going to flip it as n to the 4th times n minus 1 factorial over 3 to the n times negative 2 to the n plus 1. Okay. Now, I want to simplify this as much as I can after I've set up my formula for capital L. I want to tell you one thing to note. The polynomial terms algebraically cannot be canceled, okay? What I'm talking about is the n plus 1 to the 4th with the n to the 4th. Why can I not cancel algebraically between those?
Addition.
Because of the addition, because of the plus 1. Now, in the limit, okay, logically I understand that in the limit as n goes to infinity, that plus 1 is going to be insignificant. I understand that. But that's a limit evaluation. That is not algebra. And so what I see sometimes is people cancel out the n. They put a slash through this n and a slash through that n. Does that look like a limit or does that look like algebra they're trying to do? It looks like algebra. It looks like wrong algebra. So I would highly urge you to not cancel between the polynomial terms, okay? What I do expect to simplify are the geometric terms and the factorials, okay? Now with the geometric terms, the process that I like to do there is just to break them up into smaller pieces. With the factorials, we already talked about, the strategy is to rewrite the larger factorial, okay? So with the geometric term, we're going to rewrite the 3 to the n plus 1 into two pieces, 3 to the n, 3 to the 1. Then I have a negative 2 to the n, and I have a negative 2 to the 1, and another negative 2 to the 1. Now if you wrote that as squared, that's fine. Then I have an n to the 4th. Oh, I come to a factorial. Now the question is, do I want to rewrite this factorial, or is it the smaller one? It's the smaller one, so I'm not going to rewrite it. I'm just going to leave it alone. The goal is to try to cancel it. All right? So that's all the terms in the numerator. In the denominator, we have n plus 1 to the 4th. We have, okay, what happens when I simplify n plus 1 minus 1? It's just n. So we're trying to rewrite n factorial kind of like we did here, right? So if I rewrite n factorial, I get n times n minus 1 factorial.
What?
Was there a question up there? No? So if I cancel the ones, I end up with n factorial, and I'm trying to rewrite the n factorial because it is the larger factorial. Then I have 3 to the n, I have negative 2 to the n, and I have negative 2 to the 1. So now that I've broken everything up, let's see what cancels. So the 3 to the n's cancel. The negative 2 to the n's cancel. One of the negative 2's cancel. The factorials cancel. Anything else? Nope. So what we're left with is limit as n goes to infinity of 3 times negative 2 times n to the 4th. And in the bottom, we have an n plus 1 to the 4th times n. Can I simplify this anymore?
Yes.
Yeah, I can simplify one of the powers of n. So I can rewrite this as negative 6 n cubed over n plus 1 to the 4th. So what I did is I canceled one of the powers of n, the n to the 4th over n, into n cubed. Okay, I don't think there's any more simplification that we can do. And like I told you, for the most part, we don't expect the polynomial terms to cancel because of that addition. But when we take the limit as n goes to infinity, then we can consider some of this simplifying. And what I mean by that is the plus 1 very significant as n gets large?
No.
No. So what this limit really behaves like is negative 6n cubed over n to the 4th, if we forget about the plus 1 for a second. And what is the limit of negative 6n cubed over n to the 4th?
0.
0. Or another way to think about it is the fact that the power of n is larger on bottom compared to on top. Okay? So now we're ready for our conclusion. All right? Remember, capital L in many cases behaves like the absolute value of R from the geometric series. So in this case, since L equals 0, and what am I comparing that to? 1. The series does what? Converges. It's only when capital L is equal to 1 that the ratio test doesn't tell you anything. All right? And so what I want to leave you with is this, okay? You do not want to jump to a test, okay, just because. So I will tell you, if you jump to the ratio test on something that's similar to a p-series, okay? When we talked about with something similar to a p-series, what you should really be using is what test? Limit comparison. Try this at some point if you have time, okay? If you try to do a ratio test on something that's similar to a p-series, guess what L value you will get? 1, okay? Were you allowed to use the ratio test?
No.
Yes, you are always allowed to use the ratio test, but you always run the risk of the ratio test giving you an L equals 1. So you don't want to use the ratio test just because you're allowed to use it, because you could do a bunch of work, okay, just to find out that your L is equal to 1. So as a last note, okay, if the series is similar to a p-series, and you use a ratio test, instead of a limit comparison test, which is what you really should use, then you can expect to get L equals 1, which is inconclusive. So if you did all that work to get L equals 1, then that would be kind of frustrating, because then you'd say, okay, well that test didn't work, I have to use something else. And then you'd hopefully then go to the limit comparison test, which is what you should have used in the first place. So test for divergence, that should always be in the back of your mind. It applies in a lot of scenarios, but when it does not apply is when the limit of the terms is 0, okay? And then also, as we said in the very beginning, so I'll circle back to that, if the question is just whether the sequence converges, and we're not asking you about a series, should you be using any of the 5 series tests? No, all you should do is compute the limit and see if your limit is a number, and that's it, okay? All right, we went way over, but maybe it was a little bit ambitious to go over 5 series tests in an hour. Thank you for your attention. It was recorded, so if you need to go back and look at any parts of the video, you can. Yeah, there's a couple questions.
So like, in our last calculus class, we were supposed to do something.
Yeah.
We never got to it because they were so busy.
Right now? No, I need...
Yeah. Luckily the lesson 7 is the only thing I have left.
It'll be considered the QRC Wednesday. And hopefully it will be so you can like jump to whichever series you're
No, next week.
That's good.
Yeah.
So I want to get up to that tomorrow, but worst case I can do it.
Exactly. The worst case.
Yeah.
Thank you very much. Oh my gosh.
Okay, so you're saying the sequence goes to 0? And the question is, does the sequence
I
converge?
don't know if it's right.
Okay, then the answer is yes, because as long as the sequence goes to the number, any number, zero is a number.
I want to ask